Welcome everybody. We're going to be learning section 8.2. It has kind of a long name. It's called Constant Coefficient Homogeneous Linear Differential Equations. We are going to be learning how to solve specifically this type. Okay, so in this section, we will concern ourselves with solving differential equations of the following form. Nth derivative of y plus a1 times the n minus first derivative of y plus, and then you just keep doing that pattern, and then a n minus 1 times the derivative plus a n times y is equal to 0. Where let me write it this way, a1 all the way to an are all constants. Or let me just write it as scalars. This is what we mean by constant coefficients, okay? All of them are going to be constants. They are not functions. So this is a very special type of differential equation that we're going to see has a very nice method for how you solve it. Okay? So we can write this instead using our differential operators from the previous section. So in operator form, we can write this differential equation as P of d times y is equal to 0, where P of d is equal to, let me put this on the next line, where P of d is equal to the polynomial operator d to the n plus a1 d to the n minus 1 plus a n minus 1 d plus a n. So notice this just looks like a polynomial, right? This has a name. This is called the polynomial differential operator. So I'll just say we refer to P of d as the polynomial differential operator. Okay. We have another piece of terminology here, okay? We can actually define a normal polynomial, not a differential polynomial, by just replacing all the d's with a regular variable. So for this, we usually use what we call, or we usually use the letter r for this, okay? So this is a definition. So for the differential equation above, we refer to, so I can call it P of r, which is r to the n plus a1 r to the n minus 1 plus a n minus 1 r plus a n as the auxiliary polynomial. So that's our terminology for that guy. And then, if we set it equal to 0, we have the auxiliary equation. It's just going to be P of r is equal to 0. So we get a theorem that's going to help us play with these. So let's write down the theorem here. If P of D and Q of D are polynomial differential operators, then P of D times Q of D is equal to Q of D times P of D. So what does that mean? In particular, this means, so these linear transformations are commutative. This is a big deal. So what does this mean? This means that we could factor these guys out. So we can, in turn, so this is the end of the theorem, but let's talk about what comes true because of this theorem. We can, in turn, extend factorization of P of r to P of D. So what does this mean? So let's think about the fundamental theorem of algebra. By the fundamental theorem of algebra, I'm just going to write this as FTA. You guys may not know this theorem by name, but what it says is that we can take any polynomial and factor it, right? We can always factor it into real and complex numbers, right? So by fundamental theorem of algebra, if P of r is equal to, what does it look like when you factor a polynomial? It looks like r minus r1 to the m1 times r minus r2 to the m2 all the way to r minus rk to the mk. If we can factor it, then this means that our polynomial differential operator can also be factored in the exact same way. Okay? So what does this mean? What this means is we can actually restrict our focus to each one of these. So our goal then, or I shouldn't say a goal, maybe I should ask a question. So question, because this seems like it'll give us what we want. You know what? Let me back up a bit. Let me just say, it seems that a solution to d minus rk to the mk y equals 0 will be a solution to the entire thing. So what this means is all we need to do is figure out how to solve d minus rk to the mk equals 0. So this is our goal then. Our goal is to figure out the solutions to d minus rk to the mk y equals 0. So before we answer this question in general, I would like for us to write down a theorem, and this theorem will be extremely useful as well, okay? The theorem says if P of D can be factored to P1 of D, P2 of D, all the way to Pk of D, then any solution to Pi of D times y equals 0 is also a solution to P of D times y is equal to 0. Okay, so coming back up here, this is the guy that we need to focus on, okay? And now, before we answer the question in general, I'm going to do a simpler problem, and then from there, we're going to be able to figure out what happens in the more complicated case. So let's do an example. Let's determine the general solution to the following: y double prime minus y prime minus 2y is equal to 0. Okay. Note that this does fall into the realm of this section because all of the coefficients of the y primes and the y's are all constants, right? This is a constant coefficient homogeneous linear differential equation. Okay, so we're going to write this in polynomial differential operator form, okay? So we can rewrite this as d squared y minus dy minus 2y equals 0, or d squared minus d minus 2 times y equals 0. So this means that P of D is d squared minus d minus 2, right? This is our polynomial differential operator, okay? So let's go ahead and factor this thing, okay? So if we factor this thing, this becomes d minus 2 times d plus 1, okay? So let's solve the differential equations separately to see what happens. Let's start with figuring out what happens with this one. D minus 2 times y is equal to 0. How would we solve this differential equation? Well, what does this differential equation actually look like? Okay, this is y prime minus 2y is equal to 0, right? Or this is the same as y prime is equal to 2y. Isn't that the same as dy over y is equal to 2 dx? we can really just integrate both sides here. And so this gives us the natural log of the absolute value of y equals 2x plus c, which is the same as the absolute value of y is equal to e to the c, e to the 2x, or I can create a new constant and just write this as y equals c1 e to the 2x. Let's do the other one. How about d minus 1, or sorry, the other one was d plus 1. D plus 1 times y is equal to 0. This is the same as the differential equation dy dx, or let me write it as this, same as the other. Y prime plus y is equal to 0, which is the same as dy over negative y. Sorry, let me write it this way. dy over y is equal to negative dx. And so integrate both. We end up with ln of the absolute value of y is equal to negative x plus c, or let me say plus d, or absolute value of y is equal to e to the d, e to the negative x, or y is equal to, if I write that as c2, I get e to the negative x. What do we notice about these two solutions here? Well, think about it. I had a d minus 2 here, and I ended up with e to the 2x. I had a d plus 1 here, and I ended up with e to the negative x. Do we notice something? We're going to write down our pattern after this problem is finished. Let's go ahead and write the general solution though. Because these are both solutions, you can check using the Wronskian that they are indeed linearly independent. And so this gives us the following. The general solution is what? You can just add the two together. Okay, so you get y of x is equal to c1 e to the 2x plus c2 e to the negative x. Okay, so I'm hoping that you guys saw a pattern, right? Remember the two roots of the polynomial differential operator were 2 and negative 1, right? Think about it. If I had had just this problem, right? I had d minus 2 and d plus 1, right? And if I were to solve these for d, I would get d equals 2 and d equals negative 1, and that's exactly what showed up as my exponents of e. This is not a coincidence, guys. This is what always happens. So with this motivation in mind, I want to give you guys the big theorem of the section. So theorem, the differential operator or equation, remember the one we wanted to solve, right? Let's write it like this: d minus r to the m applied to y equals 0, where m is a positive integer, and r is real or complex. I'll get back to this complex in a second, okay? Or complex has the following m linearly independent solutions. One solution is e to the rx. The other solution is going to be x e to the rx, and then x squared e to the rx, and you keep doing that until you get x to the m minus 1 e to the rx. We didn't see any x's in front, and that's because if you go back to the last problem, these were each to the power of 1, right? And so that's why we did not need any x's. But for example, if one of them had been squared, we would also need these x terms there too. These are indeed all linearly independent. Okay? Now you'll notice that we had to talk about complex numbers, and we're going to extend our talk a little bit to talk about exactly what you do with those. Okay? Now, the idea is that when you factor something, let's go back to our factoring here, right? Okay, we said that we could factor these, right? So you factor. However, the problem is that your ri's, all of these r's, some of them might be complex numbers, right? When you factor a polynomial, you do get complex numbers sometimes. I'll give you the simplest example of this. What if you had, for example, d squared plus 1, and you set that equal to 0? Well, as you guys know, if you try to solve this equation, you actually don't get any real solutions, right? But this does have two solutions. I and negative I. Okay? So you do need complex numbers, and you need to consider that. So here are the cases, right? So there are two cases, okay? So first case, if R is real, then real valued functions that solve the differential equation are, well, we already wrote them down, but let's write them down again. Remember, it was e to the rx. Remember, we're talking about d minus r to the mth power times y, right? Is equal to 0. So if r is real, then you get, of course, what we talked about. Now, what about the second case? What about if r is a complex number? So 2. Suppose, so okay. Let me back up here. If r is complex, let's let r equal a plus bi. Okay, right? Every complex number can be written in that form, can't it? Then this means what? Complex functions that solve, let me call this star, that solve star are e to the a plus bi x, x e to the a plus bi x, x squared e to the a plus bi x. And you can keep doing this, and the last one's going to be x to the m minus 1 e to the a plus bi x. Okay? Now, you might be wondering, wow, why do I have to put a complex solution in my problem? We are kind of stuck at this time because it seems like if you get complex solutions, that your functions are going to have complex functions, right? Then, in other words, your solutions are going to be complex as well. However, there's a trick we can use, okay? The trick is to notice something. First of all, I want to remind you guys of the idea of a complex conjugate. So I want you to recall complex conjugation. First, if z is equal to a plus bi is a complex number, then we have something called a complex conjugate, z bar, which is equal to a minus bi. Okay? In other words, you reverse or you do the opposite of the imaginary part, but the real part stays the same. Okay? Why is this important? Well, it has to do with the nature of when you solve any formula or when you factor any polynomial, what do the roots look like? Okay? So, it turns out that if d minus z to the mth power is a factor of p of d, then so is d minus z bar to the mth power. Why is that? Well, this has to do with the fundamental theorem of algebra, actually, okay? Any time that you factor a polynomial, if one of the roots is complex, you are guaranteed that its complex conjugate is also going to be a root. Okay? If you really want to talk about why this is true, I want you to think about the quadratic formula, right? We know that we have this, and we have a plus or minus, and if you get the imaginary there, if you get an imaginary number or a negative number under that square root, you have a plus or minus there, and so that plus or minus the imaginary part essentially gives you the two complex conjugates, okay? So I just wanted to bring that up. Now, why is this important? Okay, here's what this means, okay? It means that z and z bar give you different sets of solutions, and it turns out that we can combine them to make real solutions. I want to remind you guys of another thing, which is a formula called Euler's formula. So let me help you guys recall Euler's formula. It's one of the nicest formulas in math. It says that e to the a plus bi x is equal to e to the ax times cosine of bx plus I sine of bx. Well, usually Euler's formula is given without the x, but with the x, this is what Euler's formula becomes. Okay? So what does this mean? I want to show you guys what happens if you take e to the... So let me actually write it like this. If we write e to the a plus bi x, we end up with e to the ax times cosine of bx plus I sine of bx. And if you do that with its complex conjugate, that's going to equal e to the ax times cosine of bx minus I sine bx. The reason for that is that when you take sine of a negative, it pulls out, but when you take cosine of a negative, it disappears. Okay? Now, what happens if you add the two terms on the right? If you add them, you get e to the ax times what? Well, these two cancel each other out. You end up with 2 e to the ax cosine of bx. So what happened? We just showed that if you add these two imaginary solutions, you actually get something where all of the i's go away. Okay? This trick would have worked even if we had an x in front. If there was an x in front of this one and an x in front of this one, we would have had an x in front of that. Okay? So let's back up a sec. Since these are all your solutions, we have lots more, right? But now we have these with minus signs. Okay? Remember, guys, the solutions of these things form a vector space, don't they? Which means that if you add any two solutions, you get solutions. So the trick then is to, remember, we just added these two and we showed that you got something real. And we can add those two, we can add those two. So the trick is to add all of these corresponding pairs of solutions. If we do that, we end up with the following. We get the following. So by adding all solutions and dividing by 2, we get the following. M real valued solutions. We get e to the ax cosine bx x e to the ax cosine of bx all the way to x to the m minus 1 e to the ax cosine of bx. Now, could we have done another trick to get m more of them? Because if you think about it, we had 2m before, but now we only have m of them. And so the trick is to subtract. Okay? So here, what I could have done instead is subtracted these two equations. So what happens if I subtract top minus bottom? If I were to have subtracted them, let's write this down here. I have e to the ax times cosine bx plus I sine bx. And here I have e to the ax times cosine bx minus I sine bx. So if I were to subtract these, what would I end up with? Well, now these cancel, and I end up with the minus becomes a plus. I get 2I sine, oh, whoops, I forgot the e. Let me not forget that. E to the ax, and then sine bx, okay? But, of course, I could just divide. If that's a solution, then that means I could divide by the 2i to get rid of it. And so we have found the other m solutions. They're going to be all the solutions with sine in there instead. And so I will say, and m more solutions. And those look like this. Okay, so what we do is for all complex solutions, this takes care of their conjugate pairs, and we actually get all real valued solutions as well. So the point is whether your roots of the auxiliary equation are real or complex, we can still find all n linearly independent real valued functions. So let's do the following example. So we want to solve, this time let's do an initial value problem. So solve the initial value problem. This one's going to be y double prime plus 14y prime plus 49y is equal to 0. And then y of 0 equals 6. And y prime of 0 equals negative 2. Okay, so again, looking at this differential equation, you notice it is a second order, but it's homogeneous, right? It's homogeneous. It's got a 0 on the right side and constant coefficients, right? So what we do is we write down the auxiliary equation, okay? So what is P of R? It's just going to be r squared plus 14r plus 49 is equal to 0, and we solve it. So if you factor this, you actually get r plus 7 squared is equal to 0. So r is equal to negative 7, but its multiplicity is 2. Okay, so what does this mean? This means we can get the solution by using C1 e to the negative 7x plus C2x e to the negative 7x. Okay, these are going to be our two linearly independent solutions. Okay, now we're not done because we need to plug in the initial condition. So the initial condition, first off, we are going to need a derivative for this. So let's take a derivative. Okay, if we take a derivative for this, we get negative 7 c1 e to the negative 7x plus, for this guy, you got to use the product rule. So we end up with the derivative of the first times the second plus the first times the derivative of the second. So it looks like this. So y of 0 equals 6. The first condition gives me the following. If I plug 0 into the first equation, I end up with c1 plus c2 Oh wait, that's not true. If I plug a 0 into the first equation, I actually get C1 is equal to 6, right? Because we actually get a 0 for the whole second part there. What about y prime of 0 equals negative 2? Y prime of 0 equals negative 2 gives me, if I plug in 0, I get negative 7 C1 plus C2, and the last one is 0, is equal to negative 2. Okay, but we already have C1, so this means that C2 is equal to negative 2 plus 7C1. And I'm going to plug in the answer that I got. So negative 2 plus 42 is equal to 40. And so this means that our solution is y of x is equal to 6 e to the negative 7x plus 40x e to the negative 7x. Okay, that would be our solution to the initial value problem. So I wanted to do this example to illustrate again what you do with repeated roots. You just throw in the extra x in there, and then from there you solve, okay? And this is what you do. You throw in the extra x, and then also for the initial conditions, make sure that you plug them in so you can figure out what they are, the constants. Okay, let's do a couple more complicated examples. So I want us to solve the differential equation. This is going to be y triple prime plus y double prime plus 3y prime minus 5y is equal to 0. So what would be the auxiliary polynomial? It's just going to be r cubed plus r squared plus 3r minus 5 is equal to 0. So we need to solve this. In other words, find all the zeros of this. Now, it's tricky, right? We don't know how to factor this exactly, but I will show you a trick, okay? The trick is you can try small numbers to see if any of them work. And one thing you can try is the number 1 to see if 1 is a root. That's always the first thing I check. And the way you can do 1 is if you add up all the coefficients of this, you notice that they do add to 0. This is sort of a trick you learn in college algebra, okay? So just to show you guys what I'm doing, since it adds to 0, I know that r minus 1 is going to be a factor of this. But to find the rest of it, I either need to use long division or I can use synthetic division. Let me just use synthetic division because why not? It's a cool technique. And so this is 1. 1 times 1 is 1. Add them together, you get 2. 1 times 2 is 2. Add them together, you get 5. 1 times 5 is 5, and 0, so no remainder. So this actually does factor into r squared plus 2r plus 5. Now try as you might, that second guy does not factor, and so we need to use the quadratic formula on this. Quadratic formula. Okay, because we do get, from this guy, we get r equals 1, but we need to figure out what the other guy is, right? So if I use the quadratic formula, I'm going to say r is equal to negative b plus or minus the square root of b squared minus 4ac. So that's 4 minus 20 all over 2a, so 2. What do we get here? Notice that we get a negative 16 under the square root, which is really 4i. So this is what we get, which is the same as negative 1 plus or minus 2i. Okay? Now you notice that these are all to the first power, right? We don't have anything squared, so we're not going to need to throw in the extra x's, but this is how we would write down our solutions, okay? So remember, this is our real part. This is our A. And our B is right here, okay? If we go back, I wrote down what to do right here, okay? These are going to be the ones that we use, but we're only going to need the first guys right here in our formula. I'm only going to need that guy and that guy because we never had to throw in any extra x's. There were no repeated roots here, okay? So here are going to be our general solutions, okay? Y of x is going to equal, we have c1 e to the x. That I get from this guy. Now from the other two guys, this is what I'm going to get. I'm going to get c2 e to the negative x cosine of 2x. Again, I got the negative x from the negative 1 and the 2x from the b is 2. And then my third solution is going to be c3 e to the negative x sine of 2x. Okay? So that's the pair that I use. So this is my general solution to the differential equation. So we've sort of seen an idea here, or we have an idea of what to do. I'm going to do a really complicated one now that's already going to be factored for us, but just so we could see what to do, you know, for a hard case, okay? So how about this? This will be our last example. Solve the differential equation. So this is what it's going to be. D squared plus 9 squared times D minus 4 times D plus 7 cubed. Ooh. What do you guys notice? What order is this? This is actually a 6th order differential equation, right? Because if you were to write this all out, that's 6 derivatives that we're taking of y. Oh wait, no it's not. 4, 5, 6, 7, 8. I apologize, it's 8th order. Yikes. Where did I get 8th order from? Well, look at the d squared. We've got a d squared squared. That gives us 4 d's, and then another d, and then another 3 d's. So this means that we're actually taking 8 derivatives of y. Seems like this would be a really complicated problem, but we've already got it factored for us. So this is really just going to be a practice problem of what to do when you have the roots already factored. So this is what we have. So if we set that guy equal to 0, let's write down our roots. We have, from this guy, we get r is equal to 4. From this guy, we get r is equal to negative 7, but we have a multiplicity of 3. And from this guy, if you were to write r squared equals negative 9, and then take the square root of both sides, you get r is equal to plus or minus 3i. And the multiplicity is 2, right? Because those roots are squared up there. Okay, so we're ready to write down our general solution, okay? Yes, you can jump right to it. So I'm going to start with the complex one since this is the hard one, right? So remember, guys, if you have 0 plus or minus 3i, then that actually means that your A is 0 and your B is 3. So because I'm going to have e to the 0x times, cosine of 3x, remember, e to the 0x is just 1, so you don't even have to write that term. So this is what we have then. We have c1 times cosine of 3x plus c2 sine of 3x. That took care of the first multiplicity, but now I have a second multiplicity. I've got to throw an extra x in there. Plus c3x cosine of 3x plus c4 sine of 3x. Everything that I just did there takes care of these 4 powers in my first complex one, right? Then I have r equals 4, so that's going to give me plus c5 e to the 4x. And then I have 3 more, all with root -7, so this is how I'm going to deal with that. c6 e to the -7x plus c7x e to the -7x plus c8 x squared e to the -7x. And this is how we would write our general solution. Okay? So as long as you can factor, you know how to find the roots of a polynomial, then you can figure out the general solution to any homogeneous linear differential equation that has constant coefficients. Okay, guys? Thank you so much for watching this video. Hopefully the next one is straightforward as well. Thank you.